Welcome friends. Now in this lecture we will solve one another type of example on determination of main dimension. Now let me first read the example. Find the main dimensions of a 3.7 kilowatt 3 phase 400 volt 50 hertz 4 pole squirrel cage induction motor having an efficiency of 85% and full load power factor of 0.84. Assume the specific magnetic loading 0.45 and specific electric loading 23,000 ampere conductor per meter. Assume full pitched winding and choose to give a cheap design. Now this is the example. Now first we will write the given data. Now you can see here the kilowatt is 3.7 kilowatt, frequency is 50 hertz, number of poles are 4, and because of the number of poles are 4 and frequency is 50 hertz, we can calculate NS by using NS is equals to 120 F by P. And if you put in this equation F is equals to 50 and P is equals to 4, then you will get the NS is equals to 1500 RPM. Then the efficiency is 85%, cos phi is power factor is 0.84, and the specific magnetic loading, that is BAV, is 0.45 Weber per meter square, and the specific electric loading is 23,000 ampere conductor per meter. Now it is given here assumption that we need to consider here the full pitched winding, and we know that for the full pitched winding the winding factor Kw is 0.955, so we are taking this value also here, that the for full pitched winding the Kw is 0.955. Now friends, if you compare this example with the previous example, then you may find there is only one small difference, and that is in the previous example velocity was given, that is peripheral speed was given, and it is asked to find the main dimensions at the given peripheral speed. Now here in this example peripheral speed is not given, and it is asked to find the main dimensions, that is D and L, which gives a cheap design. So what is the meaning of this? It means we want to find the value of the D and L such that it gives the minimum cost design, that is called as cheap design. And friends, while solving the examples related to the determination of main dimensions, remember one thing: normally the procedure up to the calculation of D square L is the same. Only change in the procedure of separation of the D and L from the D square L product. So again, as we have already calculated in the previous example, in the same way we will calculate here first D square L by using the expression D square L is equals to kVA divided by CO into NS, and as you know that the value of the CO is 1.11 into kW into BAV into AC into pi square into 10 to the power minus 3, whereas kVA is equals to kW divided by efficiency into cos phi. And now if you see the expression of this CO and kVA, all required values to calculate the CO and kVA are given. So just insert the given values in these two expressions and we will calculate here the CO and kVA. So first we will calculate the kVA. Now the kVA is equals to kilowatt. So the kilowatt is given here. The kilowatt is 3.7 divided by efficiency into cos phi. Efficiency is 0.85 and cos phi is 0.84. So if you put here kVA is equals to 3.7 divided by 0.85 into 0.84, you will get 5.18. And similarly, if you calculate the CO by using this expression, the CO is equals to 1.11 into 0.955, which is the kW, into 0.45 is the BAV, into 23,000 it is AC, pi square into 10 to the power minus 3, and if you calculate this you will get 108.7. And again in this expression of the d square L, we require the ns also, which is the synchronous speed in RPS. But it is given here in the example ns is equals to 1500 RPM. So we need to convert into the RPS. So we will divide it by 60. So the small ns is 1500 divided by 60 and this becomes 25. So just we will put in these values of the CO, ns and kVA in the equation of the d square L. We will get here the d square L is equals to 5.18, that is the kVA, divided by 108.7, that is CO, and into 25, that is the ns. And that value if you calculate, you will get 1.91 into 10 to the power minus 3. Now friends, up to this the example is same as the previous example, but now here the next step is we need to separate this d and L from this product d square L. And while separating and while calculating this d and L, we need to consider that d and L must give a cheap design. And in lecture 3 we have already discussed the separation of the d and L is totally depends on the design constraints, and there are various design constraints, and at that very constraint the value of the ratio stator core length to the pole pitch, that is L divided by tau, is different one. So just I am insert here one table which we have already discussed in the lecture 3, but for the simplicity purpose just I am inserting this table here. While solving the example, no need to write this table, but for the simplicity purpose just I am inserted here, so for easy understanding purpose. Now you can see here in that table the L by tau ratio is given. The value of the L by tau ratio is 1.5 to 2 for a minimum cost. Efficiency, if you want to design for a good efficiency, then its value is 1.5, and good overall design, its value is the 1. So but it is asked in this example, we need to find the main dimensions to give the cheap design. Cheap design means a minimum cost design, and you can see here the value of the ratio L by tau for the minimum cost or the cheap design is in between 1.5 to 2. So you can choose either 1.5 or you can choose the 2, or you can choose the value between 1.5 to 2 like 1.6, 1.7 or like that. Now let me assume here the value of this ratio L by tau is 1.5, and by taking this value let me find the value of the d and L. Now this is the only change in the previous example and this example. Now first we will find the value of the d over here. Now the L by tau is equals to 1.5, so that is our consideration. But we know that the tau pole pitch, tau is the pole pitch, the tau is value pi d divided by p, and if you put this value in the expression by L by tau, we can write the L is equals to 1.5 pi d divided by p. So as you can see here, from this equation, L by tau is equals to 1.5, means L is equals to 1.5 into tau. So if you put this value of the tau in this equation, then this equation becomes L is equals to 1.5 into pi d divided by P. And in this equation we know the P and we know the pi also. So we can calculate the value of L in terms of the D. So here you can see the L is equals to 1.5 into pi into D divided by 4. So if you calculate this, you will get 1.178 into D. And now this value of the L 1.178 we will put in the equation of the D square L here. So as we already knows, the D square L is equals to 1.91 into 10 to the power minus 3, and if you put here the L is equals to 1.178 D, so it means this becomes D square into 1.178 D. So this together becomes 1.178 D cube. So that value becomes 1.178 D cube is equals to 1.91 into 10 to the power minus 3. And now from this equation we can calculate the D is equals to cube root of 1.91 into 10 to the power minus 3 divided by 0.178, and if you calculate this, you will get the value of the D as 0.117 meter. Now as we have already find the expression of L as L is equals to 1.178 D. So just the value of the D which we have calculated here, the D is equals to 0.117, we will put in the equation number 2 to calculate the value of L. So the L is equals to 1.178 D is equals to 1.178 into 0.117, and then that is equals to 0.1378. Now before concluding your answer, as we have already discussed in the lecture 3, while separation of the main dimensions, now we are getting here the value of the D is equals to 0.117 and L is 0.1378, but we need to check these two values are correct or not, and for that purpose we are having the check of the peripheral speed. And while discussing the lecture 3, I have already told that the value of the D and L must satisfy the peripheral velocity is equals to 30 meter per second. And as we know that the peripheral speed V is equals to pi d into ns, so we will just insert here pi into 0.117 into 25. So 0.117 is the D and 25 is the ns. So if you calculate here, the value of the peripheral speed is 9.18, which is below than 30 per meter per second. So it means you can select these two values for the D and L, and the final answer becomes the D is equals to 0.117 meter and L is equals to 0.1378 meters. So similar to this, I have given one exercise of 3 numericals, and I hope you will solve these 3 examples and submit me. But regarding this exercise, while solving this exercise, I want to tell one thing. So the example number 1 is a similar type of example which we have solved in this lecture, but in the example number 2, it is asked to find the D and L which gives an overall good design. So you need to be take now here for this example. So just once again check this table. The value of L by tau for a good overall design is 1. So it means in this example we have taken L by tau is equals to 1.5, but while solving the example number 2, you have to take the L by tau is equals to 1. L by tau is equals to 1. Other example is same example, and in example 3 it is given here. So you can see here in the last line the ratio of core length is L to the pole pitch, pole pitch is the tau, is equals to 1.2. So you have to solve this example number 3 by considering L by tau is equals to 1.2. And in the third example, we are not assuming this value, whereas it is given value, so no need to check for the peripheral speed. Whereas in the example 2 also, the for a overall good design, the value of L by tau is fixed, it is not a range, and that value is 1. So again, not necessary to check for the peripheral speed. But in the given example, you can see it is asked to calculate the main dimensions at a minimum cost, but the minimum cost is L by tau ratio for the minimum cost is not a fixed value, it is in between 1.5 to 2. So here we have selected 1.5, but is that 1.5 is correct, or we have to choose the 2, 1.6, 1.7, something like that. So any value is possible, and for that purpose we need to check for the peripheral speed, and if your peripheral speed is within the range, you can go for the design. So in the same way, just solve this exercise, example number 1, 2 and 3, and submit me. Thanks for watching.